This session is about Gauss-Markov theorem. Before examining Gauss-Markov theorem, let us examine the important numerical properties of OLS estimators. OLS estimators are expressed in terms of x and y. And OLS estimators are point estimators. We get a unique numerical value for OLS estimators. And the regression line always passes through the sample means of x and y. And we know that the mean value of estimated y is exactly equal to the mean value of the actual y. And mean value of the residuals is always 0. And residuals are not correlated with predicted y, and they are not correlated with x. These are the important numerical properties of OLS estimators. Now let us examine regression model in deviation form. Yi is equal to beta 1 hat plus beta 2 hat xi plus ui hat. This is the sample regression function. And y bar, mean value of y bar is equal to beta 1 hat plus beta 2 hat x bar, where x bar is the mean value of x. Then yi minus y bar is equal to beta 2 hat into xi minus x bar plus ui hat. So let us denote capital Yi minus capital Y bar as small yi, that is yi in deviation form, is equal to beta 2 hat into small xi, x in deviation form. Small xi is equal to capital Xi minus x bar. So yi is equal to beta 2 hat small xi plus ui hat. So this is the sample regression model in deviation form, and we know that the estimated value of yi hat is equal to beta 2 hat xi, where y is expressed in deviation form and x is also expressed in deviation form. Now let us come to the Gauss-Markov theorem. The statistical properties of OLS are based on the assumptions of classical linear regression model. So let us prove Gauss-Markov theorem only when the regression model satisfy all the assumptions of the classical linear regression model. So given the assumptions of the classical linear regression model, OLS estimators possess some ideal or optimum properties. And OLS estimators are best linear unbiased estimators. That is, when the regression model satisfy all the assumptions of the classical linear regression model, the OLS estimators have some optimum properties. They are the best linear unbiased estimators. So this is the statement of the Gauss-Markov theorem. Given the assumptions of the classical linear regression model, the least square estimators in the class of unbiased linear estimators have minimum variance. So when the regression model satisfies all the assumptions of the classical linear regression model, the OLS estimators have minimum variance in the class of all unbiased and linear estimators. Or simply we can say that OLS estimators are the best linear unbiased estimators. They are blue. B stands for best, L denotes linear, and U stands for unbiased. So OLS estimators are the best linear unbiased estimators. Their OLS estimators are blue. So first let us take the case of beta 2 hat, the OLS estimator beta 2 hat. So beta 2 hat is linear. That means we can express beta 2 hat as a linear function of the random variable y. Then when beta 2 hat is unbiased, the expected value of beta 2 hat is equal to the true value of beta 2. And beta 2 hat is the best estimator of beta 2 if it has minimum variance in the class of all linear unbiased estimators. So unbiased estimator is the unbiased estimator with least variance is known as the efficient estimator. An estimator becomes best estimator when it has least variance. So unbiased estimator with least variance is an efficient estimator. Now let us prove Gauss-Markov theorem. So first let us let us prove that beta 2 hat is linear. You have to prove this always in this way. First you have to prove that beta 2 hat is linear. Then you have to prove that beta 2 hat is unbiased. Then we can prove that beta 2 hat is the best estimator. So first we are going to prove that beta 2 hat is linear. We know that beta 2 hat is equal to sigma xi ya divided by sigma xi square. And this is equal to sigma xi into small yi can be written as capital Ya minus y bar divided by sigma xi square. So that is equal to sigma xi capital Ya minus sigma xi square, and y bar into sigma xi is, that term becomes 0. So beta 2 hat is equal to sigma xi ya, capital Ya divided by sigma xi square. And let us define k is equal to xi divided by sigma xi square, where k is a weight. So we can express beta 2 hat as beta 2 hat is equal to sigma ki yi. So that means beta 2 hat is equal to k1 y1 plus k2 y2 plus k3 y3, etc., etc. So beta 2 hat is equal to sigma ki yi. That is, beta 2 hat is a linear function of yi. So beta 2 hat is a weighted average of yi, where ki is the weight. So we have expressed beta 2 hat as a linear function of yi. So beta 2 hat is linear. So we have proved that beta 2 hat is linear. Now let us examine some important properties of ki. These are the important properties of ki. Sigma ki is equal to 0. Sigma ki square is equal to 1 by sigma xi square. Sigma ki xi is equal to 1, and that is sigma ki capital Xi is also equal to 1. So these are the important properties of ki. So we have to apply these properties to prove Gauss-Markov theorem. Now let us prove that beta 2 hat is unbiased. Beta 2 hat is equal to, we know that beta 2 hat is equal to sigma ki yi. That we have examined in the last step. So let us substitute yi is equal to beta 1 plus beta 2 xi plus ui, where yi is, this is the population regression function. We are substituting that. When we substitute that, we get like this. Beta 2 hat is equal to sigma ki into beta 1 plus beta 2 xi plus ui. And when we expand this, we get beta 2 hat is equal to beta 1 into sigma ki plus beta 2 into sigma ki xi plus sigma ki ui. And here we are applying the properties of ki. We know that sigma ki is equal to 0. So the first term becomes 0. Beta 1 into 0, that term is 0. And we have already found that sigma ki xi is equal to 1. So the second term is beta 2 into 1. So that is beta 2. And from the assumptions of the classical linear regression model, we know that expected value of ui is equal to 0. So we are applying that also here. So expected value of beta 2 hat is equal to beta 2 plus, that beta 2 is a constant, so we don't have to take any expectation. So beta 2 plus sigma ki into expected value of ui, and expected value of ui is 0. So that term also becomes 0. So expected value of beta 2 hat is equal to beta 2. That means beta 2 hat is an unbiased estimator of beta 2, because the expected value of beta 2 hat, expected value of the OLS estimator beta 2 hat is equal to the true value of the population parameter beta 2. So we have proved that beta 2 hat is an unbiased estimator of beta 2. Now let us prove that beta 2 hat is the best estimator of beta 2. So first let us calculate the variance of beta 2 hat. Variance of beta 2 hat is equal to, this is the equation used to find out the variance of beta 2 hat. Variance of beta 2 hat is equal to expected value of beta 2 hat minus expected value of beta 2 hat, the whole square. And we have already shown that expected value of beta 2 hat is equal to beta 2 because this is an unbiased estimator. So in the second step, we can write like this. Variance of beta 2 hat is equal to expected value of beta 2 hat minus beta 2, the whole square. And from the last step, we found that beta 2 hat minus beta 2 is equal to sigma ki ui. So we are substituting that here. So this is equal to variance of beta 2 hat is equal to expected value of sigma ki ui, the whole square. So that means variance of beta 2 hat is equal to expected value of k1 u1 plus k2 u2 plus k3 u3 etc. up to kn un, the whole square. So whenever we find the square of sigma ki ui, we get some square terms as well as some product terms. So we are arranging all these square terms together first. So this is equal to expected value of k1 square u1 square plus k2 square u2 square etc. plus kn square un square. So these are the square terms. Then we have the product terms, 2 into k1 k2 u1 u2 plus 2 into k2 k3 u2 u3 etc. up to the last term, 2 into kn minus 1 kn into un minus 1 un. So that is the last product term. So this is, we can express this like this. Variance of beta 2 hat is equal to expectation of sigma ki square ui square, summation of all square terms. So sigma ki square ui square plus 2 sigma ki kj ui uj, all the product terms, 2 into sigma ki kj ui uj. So this is the variance of beta 2 hat. So here when we take the expectations, we can see that expectation of ui uj is equal to 0. That is one of the assumptions of the classical linear regression model. So that terms become 0. So variance of beta 2 hat is equal to sigma ki square into expectation of ui square. So we know that expectation of ui square is equal to sigma square. That is also one of the assumptions of the classical linear regression model. All the random terms have equal variance. So variance is equal to sigma square. Variance is expressed as sigma square. And so variance of beta 2 hat is equal to, instead of writing expectation of ui square, we write sigma square into, we know that from the properties of ki, we know that sigma ki square is equal to 1 by sigma xi square. So this is the variance of beta 2 hat. Variance of beta 2 hat is equal to sigma square divided by sigma xi square. So we have found out the equation for finding out the variance of beta 2 hat. Now we have to prove the minimum variance of minimum variance property of beta 2 hat. So we have to show that the OLS estimator beta 2 hat has minimum variance in the class of all linear unbiased estimators. We know that beta 2 hat is equal to sigma ki ui. So beta 2 hat is a weighted average of y's with ki serving as weight. Now let us define another linear estimator of beta 2 as follows. The new linear estimator of beta 2 is written as beta 2 star, and let us assume that beta 2 star is equal to sigma sigma wi yi. So we have already found that we have expressed beta 2 hat as sigma ki yi, and here we are defining another linear estimator of beta 2 star, which is equal to sigma wi yi, where yi are also weights not equal to ki. So expected value of beta 2 star is equal to sigma wi into expected value of yi, and that is equal to sigma wi into expected value of yi is equal to beta 1 plus beta 2 xi, and that is equal to beta 1 into sigma wi plus beta 2 into sigma wi xi. So expected value of beta 2 star is equal to beta 2 if sigma wi is equal to 0 and sigma wi xi is equal to 1. If we assume that sigma wi is equal to 0 and sigma wi xi is equal to 1, expected value of beta 2 star is equal to beta 2. That means beta 2 star is also an unbiased estimator of beta 2. So variance of beta 2 star is equal to, as in the case of beta 2 hat, variance of beta 2 star is equal to sigma wi square into expected value of ui square. In the case of beta 2 hat, variance of beta 2 hat is equal to sigma ki square into expected value of ui square. Here the weight is different, so variance of beta 2 star is equal to sigma wi square into expected value of ui square, and from the assumption of the classical linear regression model, we know that expected value of ui square is equal to sigma square. So variance of beta 2 star is equal to sigma square into sigma wi square, and then variance of, we can write like this, variance of beta 2 star is equal to sigma square into sigma wi minus xi divided by sigma xi square plus xi divided by sigma xi square the whole square. So we are adding and subtracting xi divided by sigma xi square to wi. So the sum of minus xi divided by sigma xi square plus xi divided by sigma xi square is 0. So we are, in order to prove that beta 2 hat has minimum variance, we are making some adjustments here. So we are just adding xi divided by sigma xi square and subtracting xi divided by sigma xi square. So this term becomes variance of beta 2 star is equal to sigma square into sigma wi minus xi divided by sigma xi square plus xi divided by sigma xi square the whole square. So this xi divided by sigma xi square is equal to ki, that you have to remember. So this is equal to sigma square into, we are expanding that, sigma square into sigma, we are writing the square of the first term. So we are taking wi minus xi divided by xi square together. So sigma w minus xi divided by sigma xi square the whole square plus square of this next term, sigma square into sigma xi square divided by sigma xi square the whole square. Now coming to the product term, plus 2 into sigma square into sigma wi minus xi divided by sigma xi square into xi divided by sigma xi square. So let us write the first term, that is sigma square into sigma wi minus xi divided by sigma xi square, the whole square. There is no change in the first term, so first term is there, plus we know that sigma square into sigma xi square divided by sigma xi square, the whole square. So that is equal to sigma square into 1 by sigma xi square. That is the second term. And now let us look at the third term. Third term is 2 sigma square sigma wi minus xi divided by sigma xi square into xi divided by sigma xi square. So when we multiply these two terms, we can write like this: 2 sigma square into sigma wi xi divided by sigma xi square minus xi square divided by sigma xi square, the whole square. So that is equal to 2 sigma square into wi xi. We have already defined that sigma wi xi is equal to 1. So 1 divided by sigma xi square minus, again we have xi square, that is sigma xi square divided by sigma xi square, the whole square. So that is equal to 1 by sigma xi square. So that term also becomes 0. So variance of beta 2 star is equal to the sigma square into 1 by sigma xi square plus a positive quantity, that is sigma square into sigma wi minus xi divided by sigma xi, the whole square. Now, if we define wi is equal to xi divided by sigma xi square, we know that xi divided by sigma xi square is equal to ki. If we define wi is equal to xi divided by sigma xi square, we can see that variance of beta 2 star is equal to sigma square divided by sigma xi square, which is the variance of beta 2 hat. So we can say if wi is equal to ki, that is if the weight assigned to to beta 2 star, that is if wi is equal to the least square weight, that is the weight assigned to beta 2 hat. If wi is equal to ki, if we assign the same weight, then variance of beta 2 star is equal to variance of beta 2 hat. Otherwise, we can see that variance of beta 2 star is greater than variance of beta 2 hat. So, in the last equation, we found that variance of beta 2 star is equal to if wi is not equal to ki. If wi is equal to ki, then variance of beta 2 star becomes equal to the variance of beta 2 hat. That means if there is a minimum variance least square unbiased estimator of beta 2, it must be the least square estimator. If there is a minimum variance least square unbiased estimator of beta 2, it is the least square estimator beta 2 hat. So otherwise, variance of beta 2 star, another estimator, variance of another linear unbiased estimator must be greater than the variance of the least square estimator. So, the least square estimator has the minimum variance. So, beta 2 hat is the best estimator because it has least variance. So, we have shown that beta 2 hat is the best linear unbiased estimator of beta 2 hat. That means the OLS estimator beta 2 hat is the best linear unbiased estimator of beta 2. Beta 2 hat is blue, best linear unbiased estimator. So we have proved the Gauss-Markov theorem in the case of beta 2 hat. Similarly, it can be shown that beta 1 hat is the minimum variance unbiased estimator of beta 2 hat. So we can show that both beta 1 hat and beta 2 hat are best linear unbiased estimators of beta 2 and beta 1. So we can show that the least square estimators beta 1 hat and beta 2 hat are blue. This is the proof of Gauss-Markov theorem.